Their actual scenario of techniques and methods to improve our perception of digital humans is mostly oriented to increase a likeness and interactivity inside a helpful workflow. Breakthrough milestones have been achieved to improve facial expression recognition systems thanks to the effectiveness of deep neural networks. This survey analyzes all the open and fully integrated frameworks available today. All of those can be replicated by peers to analyze their effectiveness and efficiency in real-time environments. Also, we present an overview analysis of present-day environments for digital humans that use state-of-the-art facial tracking and animation retargeting to settle a direction on the future steps in our research objectives in this field. 1. Introduction. Digital humans have become a consolidated area of research in the last 5 or 6 years. Also called embodied conversational agents or virtual avatars, they are now part of the hype cycle of emerging technologies in 2021. This visual representation of a digital human requires a diverse set of technologies and an extensive list of factors that must be achieved, such as realistic graphics, emphatic response, or a correct model that can replicate the facial expressions and performance coming from a specific real human. A wide array of applications in the industry makes digital humans part of the options to create computer-human interfaces. These include e-commerce, agent services, government communication, customer services, etc. Even the simple option of seeing a future including automated AI-based humans, with a smile and all, serving customers 24/7, makes it a relevant area of research. A small group of companies in the field has access to a fully developed framework to create digital humans with deep learning-based tracking. Such systems are based on taking a real human person, analyzing their facial performance, extracting the uniqueness of its movements inside a discrete model, and replicating it into a 3D model or avatar. A digital 3D model with a high level of detail is able to collect all the detailed animation inside a set of constraints and controllers enabling to drive a system named rig. This rig will be in charge of driving all the collected information inside the traditional animation pipeline or, for purposes of this analysis, a real-time engine. Lastly, the way humans build a particular observed link between anthropomorphism and emotional response is contemplated by the concept of the uncanny valley, and it is a crucial component inside this process to improve digital humans. All the processes mentioned earlier can be summarized as a simple phrase: framework for digital humans. There is a limited number of them that are public and open research. As the tools needed to replicate it are not easy to integrate, fully operational frameworks are rare. In order to understand how a framework for digital humans integrates different key processes, we need to split the frameworks into different areas. The first is the physical aspect of the digital human, the expression set of how this digital human performs and talks. The process ends in the real-time delivery of data, 3D graphics, using cutting-edge techniques to solve a real human face into a digital face in real time. Commonly, this is done using deep learning for prediction. The way facial expressions of a digital human are constructed to recreate all of what the human face does, when talking, expressing positive emotions or disgust, is called facial codification. The initial facial codification was standardized in the industry back in 1995, and while more than 2 decades have passed, both academics and industry are still using it as the most popular method. Facial animation parameters, based on control points codification, lacks a relation between muscles and expressions. Therefore, the use of facial expression methodologies, such as facial action code system, proposed by Paul Ekman, includes this. Popular research, databases, and methods use this facial codification. Some of them also include a validation process to certify the codification of facts with an expert demonstrating a success rate of more than 72%. Common approaches are used to improve the study, analysis, and extraction of a realistic facial codification from real-world face recognition of real subject faces. This helps to improve the validation and in obtaining information from the wild. To analyze this imagery, state-of-the-art science and computational techniques, such as including AI-based tools, is essential. This trend includes convolutional neural networks using computer vision-based recognition. Several challenges were found when developing these frameworks, and due to the increased need of the industry to achieve better, faster, and reliable digital humans, most of the key factors that the main players in the industry consider important to overcome are: the more significant challenge is to improve the quality of rendered the 3D model. This means achieving photorealism. To reduce the uncanny valley effect, some components considered are improved animation, lip sync capabilities, facial deformations, and expressions. Interactivity increases the chances of success in convincing the user of the uniqueness and individual identity of a digital human. This means the possibility of not rendering performances linearly when using real-time graphics. In perspective, with past studies and research papers trying to describe how to integrate an open framework, we explore and study the specifications, efficiency rate, and quality of the results when using state-of-the-art frameworks to complete this task. The main aspects analyzed for each framework are the facial expression recognition method, the integration of the best facial codification available, real-time control, and adequate evaluation of the emphatic response. This survey also covers the most recent tools, methodologies, and new research horizons in facial expression recognition with deep learning in the digital human field. As the main objective, this paper contributes as follows: providing in-depth analysis and formalization of the processes required of a framework for real-time digital humans. Providing a complete study of the elements covered in existing frameworks, as well as what is lacking to approach new methodologies for real-time digital humans. Providing a perspective for the future in the real-time facial tracking field of digital humans. 2 Digital Humans Facial Animation Framework. 2.1 Facial Codification and Rigs. Understanding facial animation based on expression recognition means talking about a facial codification method. The two main codification approaches are FAP and FACS. These are the most accepted methodologies in the facial animation field. FACS was proposed almost 42 years ago, FAP almost 26, and, until now, are still used to replicate avatar faces in almost any professional field inside human representation. FAP was originally designed as an industry standard to approach the fast growth of the animation industry to standardize it, and FACS was originally achieved as a theory in the field of psychology to observe, study and analyze how facial expressions describe emotions and intentions. The facial codification era in animation started in 2000s to parameterize facial controls in animated characters by video games, animation companies and studios. Several authors considered a closer relationship between FAP and FACS. FAP is oriented towards parameterizing the controls to manipulate the face like a puppet, useful for speech-driven avatars and performance animation by motion capture. FACS, on the other hand, was originally developed to parameterize emotions and their relation with muscle groups by observation. 2.2 FAP Codification, traditional rig. Over several decades the facial animation parameters methodology has become the most accepted standard for facial control of 3D avatars and digital characters. Originally inspired by AMA, was later developed by request by MPEG and became standard codification. In the field of emotion recognition, FAP has been used as the main coding system by several researchers, not just in the animation field where is more popular due to being easy to integrate, as a traditional rig as Figure 1. Therefore, a few contents in this field have been published to codify facial recognition or to be used inside a contemporary AI framework. In order to get successful and realistic human animatable faces, some authors have proposed better modeling techniques based on FAP. This includes a mixture of hand-modeled morph targets and considering how this linear animation was related to facial muscle structure, where the controls of the face were closely related to muscular descriptions. Several research results were published into Digital Humans, with a particular pioneering approach to handle skin deformation with wrinkles and bulges in combination with FAP codification. Facial expression synthesis with FAP have their research origins in the animation field thanks to some published papers, which looked for an improved way to create better effective computing interfaces with embodied conversational agents. The need to generate emotion and emphatic results while using FAP codification drove the researchers into the need to model universal expressions. This is how the Ekman theory of FACS appears in the facial animation research field for the first time. Facial action tracking with parametrized FAP was fundamental to complete several frameworks proposed to improve the use of ESA in web and mobile platforms back in 2002. As the web contents were rapidly increasing, the use of active appearance models as a statistical model-based method for estimating the 3D pose and deformation of faces in real time. This model included a geometry, pose, and texture parametrization tool inside an analysis synthesis process. Along with the 2000s, FAP codification has become increasingly popular as the main facial animation and mocap methodology with a mix of blend shapes and joints until today. 2.3 FACS codification, 3D-based scanned rigs. Early FACS codification in animation approaches became popular at the end of the 2000s in research fields due to interest. Take human 3D models from real human inverse engineering. The real muscular system of the face needed to be coded to split information of subject faces to decode it again and represent like Figure 2 shows. As soon as the methodology was reborn in the animation field, more researchers used it to validate 3D human facial models in order to improve the quality of conversational agents and standardize the rules of facial expression into it. FACS became essential thanks due to the increasing importance of 3D facial scanning in the field, as it helped to capture single shots of facial geometry, and obtain an accurate representation of muscles, wrinkles, and skin folding. Now it is a well-established technique used in movies to represent real actors in VFX. Better achievements in photogrammetry scan helped researchers separate different groups of textures such as albedo, normals, specular, etc. However, the emphatic response related to feeling less uncanny digital humans pushes the research to continuously retake the FACS methodology under new tools and new methods. Alongside better quality methods to scan facts from real people, better techniques to represent the facial movements were needed. The first attempts to include FACS codification in 3D facial rig construction allowed getting a better understanding of how the face moves, using 3D model blend shapes to generate custom controls. Hybrid methods combining scanned blend shapes and bones become the newest standard in the digital humans field. Better techniques for the interpolation of blend shapes based on FACS include some newer algorithms to interpolate traditional face models between expressions inside a contemporary framework. Some results showed a strong relationship between the color of skin, FACS, and emphatic performance on digital humans. This way, the different human expressions can be achieved realistically with easily replicated workflows. New techniques related to machine learning training models have proven the improvement of facial rig construction using information previously trained in deep learning models, making it easier to integrate into frameworks and to reuse facial animation easily. FACS validation by an expert coder becomes real in animation framework to validate rig blend shapes and expressions. In the beginning, just a small sample of 20 expressions from upper and lower face actor units was enough to let experts validate the precision of 3D face models. Later, the need to code validated FACS in linear and nonlinear motion faces became a challenging goal in computer graphics. Results about how nonlinear blending of expressions is more convincing to facial expert coders than simple linear ones. FACS databases are used to study, train and evaluate expression inside a digital human framework, were composed by libraries such as MMI with 10,000 images, DISFA with 50,000 images, CK plus 53, with 593 videos, and KEF with 4,900 images. Novel databases such as AMFD are based on YouTube content, with a large dataset of 1.8 million recordings of YouTubers in front of the camera. Thanks to web services and the cloud. Researchers, such as Benitez Quiros et al., with Emotionet, and Molla Hosseini et al., in EffectNet, annotate, classify and code actor units from facial expressions obtained from the web to get bigger and better datasets to improve new algorithms of facial research. 3. Facial expression recognition and real-time retargeting into a 3D engine. The facial tracking process, and the facial expression recognition process, has been evolving over the past years. Facial tracking to get an actor's performance into 3D animation has research papers dated from 2000, and was a basic linear interpretation of distances between points or reflective markers in the eyebrows, lips, etc. The translation movement was tracked and processed by several human hours as Vicon and Faceware. The next milestone was related to research about improving tracking in real time without human interaction, based on image-based tracking and computer vision to complete high-performance FIR. The process is made taking information from physical markers, skin marks, or directly from contours of the lips, eyes, and eyebrows using computer vision recognition and advanced methods like machine learning to recognize expressions, forecast facial movements, and retarget accurate data into the digital humans. Connection to real-time animation retargeting is part of the complete framework for digital humans under interactive circumstances. Experiments in the last years using both traditional rendering engines or game engines due to flexibility to perform high-quality graphics for a fraction of the cost of rendering digital humans. The achievement made by Ninja Theory with Hellblade, and collaboration in 2017 between Epic Games, Vicon, Cubic Motion, 3Lateral to get Siren showed the path of real-time expression recognition, and real-time retargeting into a 3D engine. Research made by Mike Seymour under Unreal Engine, has strengthened the research into Cross the Uncanny Valley with real-time interaction. 3.1 Democratized facial tracking tools for digital humans. Understanding a democratized FIR with facts for digital humans means to don't depending on commercial tools like mentioned before. This means to process all the actor's facial expressions or databases from the acquisition step, commonly related to using a 3D convolutional neural network or generative adversarial networks for this type of AI training. We will talk about tools based on different artificial intelligence methodologies, Struisk with Faxvatar, Anaja with Avatar Sim, Project Vincent, Doug Robley Masquerade, but several tools like Emini HapFax, Gilbert FaxHuman, Krumhuber with FaxCon 2.0, are not considered due to their lacking AI or their not being created to be integrated into a full fax framework. 3.2 Truly AI tools for digital human face tracking in real time with fax. Deep, Expra. Anaja's research into virtual humans started in 2016 with DeepExpra, a deep learning method to create static facial expressions in 3D characters using fax codification. The method was focused on creating emphatic cartoonish characters expressions based on two basic CNN with Gabor filters, first trained with standard databases to recognize features, the second CNN to do the same process into a 3D digital cartoon character, then, using transfer learning by HUCAPP, to create a shared embedding feature space. They fine-tuned the pre-trained CNN on the human dataset with the character dataset by continuing the backpropagation step. Finally, a fully connected layer of the human-trained model was fixed, so earlier layers were kept fixed to avoid overfitting problems. Expra? Gen? ExpraGen, later by Anaja et al. In 2018, was into 3D character fax expression generation, but the method was optimized into a 3D CNN. This end-to-end system worked in a perceptually valid and geometrically consistent manner. They trained a pseudo-Siamese network named Fused CNN composed of two branches, human CNN and shared CNN. In the last step, With a similar transfer to their past work, they trained the FCNN based on the distance between two image encodings. The final match of geometry is perceptually method matched. The last work of Anaja et al. In 2019 was related to a full framework for virtual characters, composed of a real-time recognition tool for facts, translation of values into a facial expression tool, and direct transfer into a real-time 3D engine. FaxVatar. Struijk et al. Presented FaxVatar at 2018 as the first full framework to have real-time facial recognition based on fax as an open source for digital humans. FaxVatar allows the integration of models generated by Make Human project, a full 3D environment for creating digital characters in 3D, which is integrated with the plugin FaxHuman. Several researchers developed all this suite of tools and made it open for research. This framework takes a modified version of OpenFace 2.0 as the main tool to recognize AU, eye gaze, and head rotation in real time via RGB simple camera, and process data inside a simple gated recurrent unit neural network to enable generative data-driven facial animation with Keras. It uses 17 astronomical units intensities and training with Monob mimicry database. Specially designed modules in Python with help in this framework's operation as a GUI, which controls AU's parameters and values in real time. The information between all these modules is driven using a distributed messaging library 0MQ. The development of extra features in FaxVatar allows the user to drive facial expressions with a CVS offline file, so a live human performer is not always needed in the framework. Avatar. Sim. Anaja et al. Work concluded in a full framework end-to-end named Avatar. Sim. This real and contemporary framework was proposed in 2019. Setup made with Unreal Engine and a CNN, fax, and a recognition model trained with EmotionNet, including a phoneme extraction based on the audio wave. Avatar Sim works with a simple RGB camera, recognizes 12 fax AU from the user-detected face, and then synthesizes the expression. The action unit recognizer is the same as ExpreGen, just with a small difference. These frameworks do not retarget the movements into a midway character but directly send the data to an expression synthesizer. A Python interface made in PyTorch transforms the 12-dimensional feature vector representing the probability of each AU with an average F1 score of 0.78. There is an option to use an external off-the-shelf fax AU detection SKD like Ofdex. Finally, the expression synthesizer, made in Python, drives 38 bone, 24 fax, and 19 phonetic controls in the final target digital avatar. The final character is real-time driven inside Unreal Engine with traditional blend shapes. The AI model was based on a CNN of the input image with 49 fax detection and trained with MMI, CK+, TEF, and DISFA. The result of this training model was connected to a second CNN in a pseudo-Siamese network. The second CNN was designed to recognize 10 cartoon expressions. All character expressions were validated to 70% with Mechanical Turk but not a fax expert. Both CNN, HCNN, and SCNN, inside the FCNN, were trained to get a similarity score between human and primary character expressions. Project Vincent by Giant Step. Like the work done by Digital Domain and Cubic Motion for Siren, is the case of Giant Step from Project Vincent, an experimental project of a digital human based in a private research framework, but with better results than all the ones previously mentioned in this document. Sakamoto et al. Developed an internal framework based on facial 3D scans to acquire the set of expressions with the fax methodology. Sakamoto developed a machine learning facial capture tool based on Keras and Python with a CNN model. No external database was used for the neural networks, as information was taken from just one face and all the possible expressions. The framework uses two neural networks. First, A facial marker tracker was designed to find and predict the coordinate system of 3D markers with marker-less 2D images of facial expressions. The face was segmented into 6 areas, and every area learns separately with 35 expressions to have a total of 210 different blend shapes of the face. A second neural network, designed as a blend shape mapper, was connected with the 6 areas to find an appropriate blend shape intensity for the AU with the information of the 3D marker coordinates. Final results are delivered in real time to the 3D model inside Unreal Engine. Masquerade by digital domain are one of the newest unsupervised AI methods. Private solutions made by cutting-edge companies like Digital Domain to improve the quality, realism and to drive emotional characters such as Thanos in the Avengers Endgame movie. They have been testing GANs to train and facial recognition. Above the CNN methods, some researchers have chosen a generative adversarial network to complement their tools. Few details are public about this project than a couple of neural networks take the role of recognizing markers painted in the actor's face. Later, the solution is complemented with another set of AI tools to train data like CNN and label it and predict like the other solutions before studied. 4 results of the state of the art. This section discusses and analyzes the state-of-the-art frameworks reviewed, the importance of facial codification methodologies, and how they become important inside tracking faces to drive digital humans in real time. 4.1 Discussion on codification for real-time tracking on digital humans. Native FAP codification is not considered in the field of study of this article, but we considered as a common solution used in traditional keyframe animation. Important solutions like ARKit from Apple, the most adopted solution due to the democratization of RGBD cameras inside Apple phones, have 51 basic coded expressions but are not considered a tool to customize or modify. Professional solutions in digital humans like Faceware and Dynamixes, based on 48 and 47 coded expressions, cannot allow custom expressions or modify them. These tools, being commercial-born, have become extremely popular around the world. As we analyzed previously, the use of an expressive emotional solution oriented to drive facial performance in digital humans adds extra fidelity because it matches with real 3D scanned humans, whether the accessibility to access facial database to train the AI model results in the digital human. Using FACS as a codification method to classify facial expressions has become common in the computer graphics field. But there is no customization and parameterization in commercial solutions. FACS generation tools and solutions are available using it, but the lack of full frameworks options makes it more interesting to further research. 4.2 Discussion on digital humans and open frameworks. We studied options that begin as simple facial expression recognition and transferred knowledge to digital avatars to complete solutions with real-time tracking into live 3D digital humans. All the options analyzed were based on FACS codification as a basic way to understand the human face. Several frameworks and solutions were discarded because they were not oriented to this methodology. As well, discarded solutions just made to extract FACS like XpraGen, FACSCAN and DeepXpra were not related to this survey, as you can see at Table 1. An important part of the research was to cross-match frameworks, FACS and digital humans, showing the importance of validating FACS working with certified coders in some parts of the process. Different frameworks were subject of FACS recognition test protocols with test subjects to compare the recognition rate presented in all the frameworks and tools. Not all the frameworks studied included the results of this test. A certified coder was used to validate the codification of input/output on the models in HAP-FACS, FACSCAN, with the highest recognition rate, but was also discarded as being a generator and incomplete framework, respectively. Some of these, like FACSVatar, DeepXpra had results up to 89% of recognition rate for the MFACS model, but, is important to clarify, is not certified by coders. Suppose we filter all the options to determine the complete open frameworks with an updated state today. In that case, we will find a niche interesting to research with certified coder validation, deep learning based, and the highest recognition rate. 4.3 Discussion on future work. The high demand for solutions for conversational assistants, chatbots, virtual influencers, streaming video hosts, etc., combined with the expectation to democratize the use of these tools, will cause more options to push the industry to have improved solutions. The need to research to have democratic options of frameworks, with documented solutions for the right way to get scanned persons, AI models, trained databases will be predominant. By March 2021, Epic Games had released the initial version of MetaHuman Creator, a tool created to help independent and small studios easily create digital human assets with photorealistic results. This tool represents a huge leap in the democratization of digital human tools, but the lack of two-input custom face scans to create a digital human based on a real human shows the limitation of this tool and how there is still a long road to place custom facts in easy-to-use tools such as MetaHuman. Research and development in real-time facial tracking solutions, with easier and affordable options, aligned the same way to improve the democratization of these technologies, is an essential direction. The starting point is better portable devices as HMC with computer vision, from a fraction of the cost and open to be customized are the starting point. If we consider the last standardization for a facial codification was the one made by the MPEG group, without an updated version or new alternatives, we can deduce that it is time to generate newly standardized protocols for fax methodology. Standardizing modern facial codifications based on emotional expression and skin/muscle activity is another direction of research. Proven methods should be analyzed, while correctly documented protocols and data labeling homologation are other topics to research. 5 Conclusions. We have reviewed digital humans' main concepts and elements inside a real-time rendering framework to introduce deep learning facial tracking. The analyzed frameworks for real-time digital humans provide a wide study of the elements covered. The review of every step to distinguish limitations and advantages let us check and compare actual options. Future steps will include the test of each solution to compare effectiveness with Unreal MetaHumans, and prototype a custom fax and CNN-based tracking inside a validated fax codification. Future research and experiments in this field are priority to our research group.